we have learned about regulated lemma and embedding lemma. And embedding lemma shows that this concept of epsilon regularity is useful for finding a subgraph. And in fact, we can find many copies of subgraph in G. Not only just one copy, but many copies. So for example, the following triangular counting lemma works. So let's say you have a graph G and its vertex set is again partitioned into say 3 parts, and its pair is again epsilon regular. So this pair Bi Bj is epsilon say Dij regular. So we indicate the density as d sub ij for all I and j between 1 to 3, and let's say epsilon is small. So technically, I mean, you don't have to say that. Then what we can do is that we have this epsilon regular pair, epsilon regular pair, epsilon regular pair. Then using embedding lemma, we know that it has many triangles. But more than that, we can talk about the number of triangles. The number of triangles, say V1, V2, V3, where each Vi comes from this set Vi, is roughly as expected. You multiply these 3 numbers, and then some large number, I mean, say 10 is enough, times epsilon, multiplied by the number of vertices in V1 times number of vertices in V2 times number of vertices in V3. Okay, so what's this number? So imagine again that you have random graph instead. So you have this set, and then for each pair you add an edge with the probability, say here, probability T12, probability T13, and probability T23. And what's the probability that for this triple, what's the probability that you get a triangle? That's exactly this multiplication of these 3. So there are this many triples, and each of them has probability of becoming triangle with this. So if you prove it with high probability, you can actually show that the number of triangles is concentrated around this expectation. So that with high probability, it's here. It could be slightly larger or slightly smaller, but it's more or less close to this number. And what is said is that this concept of epsilon regularity is legitimate pseudo-randomness. Once you have that property, then it behaves like random graph in this sense. And okay, so this we don't prove. Proof is just consider the proof of embedding lemma and then use it, and then to actually count the number of triangles, and you can get it. So we'll not prove this here. I leave it to you as an exercise. So this is a useful thing, and using this, we can prove the following lemma, which is called the triangle removal lemma. So what's it say? What it says is for all epsilon positive, there exists some number delta such that the following hold. If you have any n vertex graph, if it has at most delta times n cubed triangle, so not so many triangles, then this graph can be converted into a triangle free graph by removing at most epsilon fraction of the edges. Okay, so at first you might think that what's this statement? I mean, it feels a bit weird at first. Okay, but why is it useful? We will later see that there are many applications of this. I mean, I will show you at least one application, but in fact, there are many applications of this type of removal lemma. So essentially what it says is that if you have many triangles, then it's far from being triangle free. I mean, sorry, the other way around. If you have a very small number of triangles, then you are very close to the triangle free. And if you are far, I mean, as a contrapositive, if you are far from being triangle free, then you must have at least a certain number of triangles. So this is by measuring how far your graph is from triangle free by making edge changes. So by deleting edges, how many edges do you have to delete to become a triangle free? So that's kind of distant from triangle free graph to your current graph G. And this is number of triangles that your graph G had. That's also another way of measuring how far you are from triangle free graph. And this triangle removal lemma states the relation between them. Okay, let's first prove. So assume if delta is much smaller than epsilon. I mean, let's just assume also this epsilon is small, say 1/1000. I mean, if you know the statement for epsilon being 1/1000, and you automatically get the same statement for smaller epsilon and bigger epsilon. Okay, so you have a G. Again, suppose that your G has at most delta n cubed triangle, and G has n vertices. Then we apply regularity lemma to obtain the epsilon to the 4 regular partition, the B1 to BR, which also satisfy the, I mean, there were so there were conditions with which is equitable partition, we can assume, and this R is say at least 1/epsilon to the 4, and then this at most say T, which can be taken as power of epsilon to negative say 20. And what we do is we consider the epsilon to the 4, epsilon reduced graph R of this partition. Then what we can say is that this reduced graph is triangle free. So your original graph has so small number of triangles, and that kind of inhabits to this reduced graph in a way that it doesn't have a triangle at all. Why? If R contains a triangle, say I, J, K, then what? Then by the triangle counting lemma, it states that there are at least epsilon cube. So its biggest graph means that the Vi, Bj, Bk, the density between them is bigger than or equal to epsilon, bigger than equal to epsilon, bigger than equal to epsilon. So epsilon cube minus 10 to the epsilon 4 times Vi times Bj times Bk. And what do we know? This number is at least, say, epsilon to the 4. Each of them has size at least n over r. So you have this, but what? R is bounded by this number. And when we choose this delta is much smaller than epsilon. So we could have taken something like this small. So this is much smaller than 1 over t. So this is what? Epsilon 4 over t to the 4 times n cube. And t is chosen in this way, and delta is chosen this way. So this is what? This is at least, bigger than delta n cube. So this many triangles are found, which is a contradiction to the assumption. And this R contains no triangle. So small triangle condition inherits to this reduced graph R so that they get triangle free. And now we analyze the meaning of this being triangle free, and then we will convert this into the information about how many edges do we have to change, do we have to remove to make it triangle free. So how do we do it? Now we delete edges to make G triangle free by deleting everything. So we leave all the edges which are inherited to R, and we delete every remaining other edges. So we delete edges between the Pi and Bj, where this Ij is not an edge in R. Then what? What do we have to do? Delete. We delete edges inside each Pi. We delete edges between Pi and Bj, where this is not epsilon to the 4 regular. And we delete edges between Pi and Bj, where the density between them is smaller than epsilon. So that's because of the definition of this reduced graph. And what? How many edges we delete? For first, we delete the most n square that are summation of Pi square, which is n over r square. I is 1 to r, so which is n square over r. That's smaller than some small number epsilon to the 4 times the n square, because we have this. And 2 is what? You know that there are at most epsilon times r square pairs, which are not epsilon to the 4 times r square pairs, which are not epsilon to the 4 regular. And then all of them have size, what? Almost this many edges between them. Okay, so this is what? Epsilon to the 4 n square. And the third case, there could be r to the 2 pairs at most. And each of them has what? Epsilon times n over r square edges between them, because its density is small. Then what do you get? This is what? Epsilon over 2 n square. So you add them all together, we have deleted at most epsilon n square edges. We know that epsilon is small, so this summation is smaller than epsilon. So after deleting this, if the resulting graph, so we delete this one edge from G, if the remaining graph contains a triangle, then only possibility is that we delete every pieces. Only possibility is that there is a parts pi, bj, bk, such that, say this triangle is xyg, then x is in pi, y is in bj, c is in bk, with this ijk is a triangle in R, which is a contradiction. Thus, the graph becomes triangle-free after removing this epsilon n square many edges. So this proves this removal lemma. Okay, but why is it useful and important? Let's see some application of this lemma. And one of the problems we are interested in, hypergraph theorem problem, is the following. Let's say this be the collection of R graph, R uniform graph, hypergraph, with the S axis and most B vertices. So which is a collection of graphs which are at least as dense as certain threshold. The number of edges is fixed, but the number of vertices is small. So this consider all the configuration where the edges are cluttered. They are cluttered together. And one natural question raised by Brown and Roche is that they define this function as extremal number of this configuration, this collection. So if your hypergraph has no small parts where the too many edges are packed there, then how many edges can you have? Brown, Erdős, those in 1973 proved that this value is at least some constant times n to the rs minus b divided by s minus 1. And how do they prove this? This is using probability construction. Basically, you do deletion method, then you can prove this. So in fact, this implies that if b is s times r minus 2 plus 2, and if you just plug that in, then what? You get that this is quadratic. And Brown and Ellis shows conjecture that this is type, meaning that if you lower it, if you make it higher, if you increase by just 1, and this is literal of n square for all r and s at least 3. And they further conjecture that this is not just for 김영락. Okay, so this was wrong, that this is t. So this is literal of n to be t for r being bigger than t, and t is at least 2. And so this is a major open problem, and only case that that's known is when you have r and s is 3 here. So this is something called the Rujak-Demoredi theorem. They show that when you have s and r being both 3, then this conjecture holds. This is also called Rujak-Demoredi theorem or 6-3 theorem. And you can prove this using the triangle removal lemma. So if you see, you are considering 3 from hypergraph, and when 3 edges and most 6 vertices, if they are totally disjoint, then it's 9 vertices. And if they are just sharing one vertex, then what? This is 7 vertex. So these are okay. When does it become non-okay? If 2 of them share 2 vertex and then 1 vertex here, then this is not okay, 6 vertex. Or if you have 3 sharing vertices in this manner, that's also not okay. So we want to get rid of this. And get rid of the first one. And we want to construct, we want to make sure that if you have too many edges, then we must have these. So let's prove this. Let's suppose that there exists epsilon such that this is bigger than epsilon s squared for infinitely many n. Then let delta be the number that we obtain from the removal lemma. And with the above choice of epsilon. So, meaning that if you have a delta n cube triangle, then they can be made triangle free by removing most epsilon n square edges. So that's our choice. then there exists the sufficiently large n and n vertex 3-uniform hypergraph H with the number of edges in H is at least epsilon n squared, and that contains no copy in here. So no 3 edges, hence n more 6 vertices. So first, we can assume that this does not happen. So if this H contains 2 edges, E and E prime, with the intersection size at least 2, exactly 2, then what? So once you have this, your third edge does not intersect with this. Otherwise, you get this configuration on 3 edges and 6 vertices. Then, no other edge intersect E union E prime. Otherwise, you get the forbidden graph. Thus, whenever you have this, you can just simply delete this because everything else is there, and then there are no other edges. So, whenever there are 2 edges intersecting at 2 vertices, we remove them. We remove these 4 vertices. This results in a smaller graph. You have the n prime vertex graph. And let's say G with what? At least epsilon n squared minus how many edges have we removed? Every 4 vertex, you remove 2 edges, so at most n over 2. But that's at least n times epsilon prime squared. So, we know that n is sufficiently large, much larger than 1 over epsilon, so this holds. So, we can assume that this G is a linear hypergraph, meaning that whenever you have 2 edges, their intersection is at most 1. So, we consider G prime be the shadow graph. What does it mean? Whenever you have a hyperedge, you consider its shadow, meaning that you consider all the pairs inside of this. And then you add this and edge. So you replace this hyperedge with the triangle there, and then you obtain graph with the edge set UV, such that there exists E in G, such that UV is a subset in with E. And in G, so now what? We want to use the fact that this doesn't happen. So this is a triangle, this is a triangle, this is a triangle in G, and this is also a triangle in G. But these 3 directly comes from the hyperedge, but this does not come from hyperedge. So this configuration can be converted to the triangle that does not come from an hyperedge. So in G prime, there are 2 types of triangle. The U1, U2, U3, that depending on whether they come from an edge or not. And for the first type that come from the edge, the number of triangle from the first type is almost what? No, at least. At least, I mean, it's exactly same with the number of edges in this G. And we assume that that's at least epsilon times n prime square. Furthermore, and they are edge disjoint triangle. Because your hypergraph was linear. So you have an edge disjoint triangle. There are this many. Guess what? Thus this G prime cannot be made triangle free by deleting less than epsilon n square edges. So the removal lemma, the counter positive of removable lemma says that if removal lemma says if there are not many triangles, then you can make it triangle free by removing small number of edges. But counter positive is that if you cannot make the graph triangle free by removing less than this many vertices, then you must have many triangles. Implies that its G prime contains at least delta times m cube n prime cube, which is bigger than epsilon n prime square. I mean, this is actually much bigger than n prime square. Triangles in G prime. But what? This is the maximum number of edges in your linear 3D graph. That means there must be a triangle coming from the second type. So there must be a triangle that does not come from the hyperedge. Thus G prime contains a second type of triangle, U1, U2, U3, where there are 3 edges, E1, E2, E3, such that the U1, U2 is holds. A UI, UJ, a subset of EK with IJK being 1, 2, 3. However, then what? This case, if you collect these 3, then you have 6 vertices, or 3 edges. That's from the graphing here, a contradiction. So this shows that if you have a 6, 3 here, and this is real of R square. So this proves the Roosa-Femoretti 6, 3 theorem. So this is a statement in hypergraph theory. And it has an application. I mean, it has many applications, but we can consider one application in number theory. And maybe we talk about that in the next video. Okay, I'll see you in the next video then. Thank you.